The session, let me give a brief introduction about me. So, so again, my name is Chamod, and I work as a software engineer in an Australian company called Industrial Software Group. And other than my technical background, I run a few communities in Sri Lanka, which are KCD Sri Lanka and Golden Sri Lanka, GitHub, and I'm also a GitHub campus expert. So, and I'm leading DDG Sri Lanka as well. So, uh, so these are the things today I'm gonna discuss about. So the first one is what are the containers, and then what is GitHub Container Registry, then why GitHub Container Registry. Then I'm gonna move into the what is Kubernetes and give a brief introduction about Kubernetes. Then what are the benefits of using Kubernetes, and yeah, we move into the demo and the Q&A. So, so what are containers? So containers are packages of software that contain all the necessary element to run any environment. So it doesn't matter what's the environment. It can be run if on Docker. So as you can see in this meme, uh, so previously, before coming into the container technology, people have to set up everything from the sketch to run a certain application. For an example, let's say we are running a Java application on production. We have to set up it for, we have to install JDK and everything to run a Java application. But if we containerize the application, we can run it anywhere because it's easier. So let's move to the uh, container registries. So GitHub is not the only container registry offering platform. Actually, GitHub is a source repository management system previously. Now they are coming into the GitOps. And there are other container registry offering platforms like Docker registry, and from Google we have GCR. It's Google Container Registry. In Azure we have Azure Container Registry, uh, and AWS got another one too. So, so what are the benefits of using GitHub Container Registry? So the key benefit is it reduces the maintenance by keeping all the everything together. So which means we can keep the source code and the build as well as the distribution in the same place. So before we talk about the need of Kubernetes or container orchestrator, uh, do you know the meaning of uh, monolith and microservice? Can someone tell me? Yeah, that's correct. So as he said, monolith run as a a single application, but in microservice we can split the application into a different parts and run it as a same one. And it's easier to maintain and easy to do everything and deployments as well. So when it's come to the managing containers, we cannot do that in manually. Let's say our application got 1,000 containers. How can we manage? So that's the main reason Kubernetes coming into the scene. Because of the Kubernetes, we can manage, actually orchestrate so many containers at the same time. So as you can see in the from the definition, Kubernetes is originally developed by Google, but now it's maintained by CNCF, Cloud Native Computer Foundation. Yeah, let's move into why we should use Kubernetes. It's actually highly available, which means simply means application has no downtime, and they are available for 24/7 and accessible to every user, and it's very scalable. So with a need of resources, it can be easily scalable to we can maximize the resources. So when it comes to the Kubernetes, there are some few things you need to know. The first one is nodes. Nodes means worker machine that runs container. Actually, we don't need to have a cloud environment to run Kubernetes. We can do it in physical machine or even hybrid or cloud. So the second thing is pods. Pods are the smallest deployable unit in Kubernetes, and the next one is deployments. It's actually it's provide a declarative updates for pods. So when we do a Kubernetes deployment, it's actually creating pod. So the next one is service. We can use services for expose our application to external or internal. And if our application has some secrets or configuration stuff, we can use config maps or secrets. And the another one is namespaces, because namespace provide a way to divide our cluster into a different parts. Yeah. So this is actually a Kubernetes object YAML definition. So as you can see, first we have to specify the kind. So this is a pod YAML definition. If it is a deployment, the kind name, kind value will be a deployment, and the most of the other parts will be same. And as you can see in the image, we can put the image name where the image is located at, and as well as we can specify the port of the image. So actually we can run more than one container in a single pod. So there are two ways to create a Kubernetes object. The first one is imperative. That's my personal favorite. Actually, we need to install the Kubernetes CLI into our machine or whatever the environment we are in. Then we can run some command and create Kubernetes object very easily. And the other one is the declarative way. Maybe we will have to remind this definition, or we can go to the Kubernetes docs and copy and edit. Then we can do the create Kubernetes object. So I will show a quick demo about building a image and doing a deployment in Kubernetes, as well as exposing it to the outside. So here I have pre-prepared a simple Go application, which yeah, hello FOSSASIA 2023 when we hit the API call. So and I have actually Dockerize it in here, and I'm actually using a GitHub action. I have pushed this image to GitHub container registry. So let me show the uh, GitHub action for that. Actually, you just don't need to add anything when you're doing this. You can go into actions and new workflow. There are tons of templates available, so you can easily do that. So as you can see. So now I'm going to do a tag release. So the action, GitHub action will be triggered, and it will create an image and push it to the GitHub container registry. So I'm going to name it as version 3.0. All right. So now as you can see, a GitHub action is running. Since we have only few minutes left, I'm not waiting till this end, and let's move into the Kubernetes cluster side. So create a Kubernetes cluster. I'm using a Google Cloud Platform, and you can use any cloud provider you want. You can use either Azure or AWS. So using this setup, you can easily create a Kubernetes cluster. It's very easy to set up. So I have actually created the autopilot one because I don't need to specify the nodes. Depending on my workload, the the Google autopilot will take care of the creating and deleting the nodes. So here's my created cluster. When I want to access to Kata, I need to go to the connect and copy this command, and yeah. So I'm going to run this command in the Google Cloud Shell because it is very easier to use, and it's running on cloud environment, so it's very fast. So I'm simply pasting the command. Okay, I have already pre-prepared all the declarative commands to uh, run my deployment. So to view the all the namespaces, I need to hit kubectl get ns. Okay, I have only default, and the other kubes namespaces are created by the kube system. So let me create new namespace. To view the NS. So as you can see, dev namespace is here. So let's create the deployment. So when I hit this deployment creation command, it will create a deployment under this name, FOSSASIA-2023. So here I'm specifying the port and the namespace as well. So I can actually view the deployment in here by running kubectl get deploy, and I have to specify the namespace as well. So yeah, as you can see, it's not ready yet. Which means it's still the deployment is creating. So when it's come to exposing this deployment to outside, we can use this command kubectl export deployment, and we have to specify the type as a load balancer. Okay, so everything command is I have added in this Git repository. I have shared it later. So let's move forward to the slide in my presentation. So where to next? So if you are new to Docker, you can try Docker and GitHub Container Registry and Kubernetes. So if you want to do some labs about Docker, you can go to the Play with Docker website and try out. Actually, this is the place where I've learned about Docker most of the time. And if you want to upskill your GitHub skills, such as GitHub Actions and GitHub Container Registry, there are those tutorials are available in skills.github.com. So if you don't have cloud credits, you don't need to worry about that, because you can always use Minikubes. It's a local cluster. You can practice Kubernetes in your local computer. And so other than that, you can stay in touch with my communities, Kubernetes Sri Lanka and KCD Sri Lanka, to learn more. So do you have any questions? Feel free to ask. Actually, for the free users, they offer 500 MB, and if you are pro user, they will offer 2 GB. Okay. So thank you. You can follow me on my social media.
Thanks, Shamod. It was really wonderful session. I do remember earlier we used to say no life without water. If you ask a developer, he will say no life without Git. So, okay, we'll be back with the
Nginx or like any other API gateway. Okay, let's start with authentication and security. So within API gateway, when a user sends a request to your service, that is your API gateway, you can set up authentication. So this can be simple stuff like a key value pair, JWT token, or you can use other platforms, other third-party platforms, something like OAuth or any other third-party tool. So it not only lets you control who access your APIs, but you can also get the user info once the user is authenticated with your API gateway, and you can make your API a bit tailor-made so that you can give each user a tailor-made experience. Another one is rate limiting. So rate limiting can be intentional, something like denial of service attacks, or it could also be unintentional. So maybe like your site got really popular, your application got really popular, and there are a lot of users trying to access your application at the same time. So this could happen in a multitude of ways, but you have to make your services reliable enough to work against this, right? So an API gateway can help you do that. So if the number of requests exceeds a certain threshold, you can choose to reject or delay the request so that your backend application or your actual APIs can handle those requests. Now let's look into monitoring and observability. So you are only as good as your monitoring solution, because if something happens, if some error occurs, or if there are some issues, you need to be able to identify it. You need to be able to have data on it to actually protect against it. So an API gateway like Apache API 6 integrates with a lot of observability tools, so like tracers, so things like OpenTelemetry. So API 6 integrates with OpenTelemetry and loggers. So you need logs coming in from your API gateways, from your backend applications, and you also need metrics. So stuff like Prometheus, it needs to be integrated with stuff like Prometheus. So all of these stuff can be handled centrally within an API gateway. So when you think of a system without an API gateway, you need to actually add all of these into each of your applications, each of your microservice application. So an API gateway makes it much easier to do that. Another aspect of reliability is version control and zero downtime. So you have to make sure that you are able to bump new versions, release new version of your application without your users experiencing any downtime. And you can do this with something called a canary release. So this is a release strategy that is being followed in like the software engineering world. So you have your V1 1.0 API, and you are trying to switch it with a V 2.0 API. And initially, you have all of your traffic being routed to V1.0. So API gateway is routing all traffic to V1.0, and you have V2.0 deployed in your server. And initially, you can route some traffic. So 5% is a nice number. So you can route 5% of the real traffic to your new version of the application, and the API gateway lets you do that. So in Apache API 6, this is handled dynamically. So you don't need to like restart the gateway to make this change, but some percent of the traffic is now being routed to the V2.0 application. So so you can test your application with real traffic, but you are only testing it with a small percentage of the traffic. So if any issue occurs, or if your application is not working as you intended, or if there are any bugs, you can easily identify it without affecting most of the users. And finally, when you have tested the new version of your application, you can deploy or you can configure the API gateway to route all traffic to your new version of the application. And there is always an option to roll back to the older version of the application if you have an API gateway. Next up, we have circuit breaking. So this is similar to how circuit breakers in electrical circuits work. So the main goal of a circuit breaker in an electrical circuit is to like protect your applications from faulty components. So if you have a faulty service or if you have a service that is experiencing some downtime, you need to cut it away from your system. If you don't do that, what happens is like it can cascade into other services. So if upstream A1 is not working and you are still trying to send requests to this upstream service, these requests will fail and this will cause a bottleneck in your system. So you have to make sure that you cut it off from the system. So an API gateway can check the run health checks with these backend applications, and if they are faulty, they will cut it out from the system. And the API gateway can keep polling the system, and once the service is back online, it can restart sending requests to this service. And finally, redirects. So as I mentioned in the beginning of the talk, reliability not only means reliability of your services, but also means reliability for your users, for your client applications. So redirects are a way to do that. So if you are deprecating or like if you are changing your API endpoint, a client application might need to change their endpoint as well. So this is an additional overhead to the clients. So if you are doing this frequently, you don't want your clients constantly changing their code to like work with your API. So an API gateway acts as a middleman, and even if the user sends the old API endpoint, an API gateway can redirect the users to the new API, and it can also send a deprecation notice with a 300 status code. And this will help users to like transition to the new API in a more smooth way. All right. And before I go, like I want to talk about the project and the community. So Apache API 6 is a project under the Apache Software Foundation, and it is entirely built by the community. So the Apache Foundation has this motto of which can be summed up as community over code. And this project is entirely community driven. And we have community members from around the world. So yeah. And if you're interested in contributing to API 6, feel free to do so. So contributions of any kind are welcome. You can contribute code. You can help us by testing out API 6. You can share how you're using API 6. You can help us write blog posts or give talks like this. So you can check that out as well if you are interested. And if you have any questions, feel free to ask me now. And you can check out API 6. And there is also an article version of this talk. So if you want to look at all these diagrams, you can check that article out as well. Yeah, thank you. I guess I have a lot of time for questions.
So we do have question.
Okay, no worries. Yeah, so my question is basically, I'm trying to basically find out what exactly this is, why this is different from load balancing. It seems to be a lot of features are very close to load balancing, except for things like the monitoring and the logging. But does it do things like integrating multiple APIs? So is that like one of the features that it has, or is it more like it's quite a more advanced version of load balancing essentially?
Yeah, like it does load balancing. So load balancing is I guess it's a superset of what a load balancer is. So an API gateway can do load balancing, an gateway can also batch requests as you mentioned. So one request to the API gateway, and the API gateway will send multiple requests back to your services, collect all the information, and send it back as one package. So it does all of that stuff, but it also gives you more features on top of that, better control of your traffic. Yeah. So. Um,
Yeah, so I have a related question. So you mentioned it has tracer support, right? And I wonder when this API calls the downstream API, and if you also use the same API gateway for those downstream APIs, does the tracer integrate all the trace together? And yeah, can you get into the detail like how the tracer works?
So the API gateway acts as the entry point to your whole backend services. So when we talk about OpenTelemetry, like this is where an API gateway is the place where you get the trace ID generated. So everything that starts at the API gateway, it can track. So if you have instrumentation in your backend applications, the API gateway can trace the whole request. So from your API gateway to your service, and if you have databases, maybe you can also instrument those databases to send out traces. So an API gateway can be the central point, and it collects all these, and you can get it as a single data. Yeah.
So there are many API gateway service on all the platform. If you talk about AWS, they have AWS API gateway. In the Google also, Google APIs and all. So have you done any kind of evaluation like this API 6 from Apache, how it is different from them? What is the USP it is having, which is basically a differentiator as per the other API gateways? What are those points, those brownie points actually, that would be really helpful if you can help us?
Yeah, but that's a good question. So first of all, API 6 is completely open source, and it is hosted by the ASF, so that's a big point. And then like API 6 is built on top of Nginx, but it is a different build of Nginx that makes it much faster, much more dynamic, and much less, and cost much less overhead to your infrastructure. So being fast and makes it really scalable. So as your applications grow, I'm talking in the range of millions of millions of requests per second. So in such scenarios, API 6 really shines compared to other alternatives. And when you talk about big cloud providers, you can always end up in scenarios like where you are tied to the vendor, but Apache API 6 like lets you get away from that, because like you can easily switch to a different API gateway if you want, because API 6 supports a lot of common specifications. So like if you're using Kubernetes, there is a Kubernetes ingress API, and there is also a Kubernetes gateway API. So API 6 supports all of these. And even if you decide to switch API gateways, you don't need to change your configuration. And APIs, and like this will work seamlessly. And there is also the case for multi-cloud or like hybrid cloud scenarios where you don't necessarily want to like be tied to one cloud provider, and a gateway like API 6 can like help you avoid that. Other questions? Oh. Okay, so API6 has this plugin architecture. So there is the core API 6, and all of these features, all of these things like rate limiting and observability are implemented through plugins. And let me just show you the docs. We have multiple uh, plugins for rate limiting. So uh, yeah. So this plugin limits the number of rate limits based on number of requests. And we also have things like limit the number of simultaneous connections a user can have with the API gateway. And you can also do things like limit based on count. But you can also make it more complicated by setting up rules for specific users. So you can set up authentication, and once the user is authenticated, you can give them a certain limits. So this particular user has 60 can make 60 API calls in a minute, or like a paid user can make 600 API calls in a minute, or something like that. So API 6 really lets you do that. And if you have a more complex scenario that is not supported within API 6's plugins, you can also create your own plugins. So you can use Lua, or like you can use all of these other programming languages. So API 6 also supports multiple plugin runners. So if you can write Java plugins, you can write Go plugins. We are also working on a WASM integration. So basically you can write a plugin in any language and port it to WASM and like run it with API 6. So yeah. Yeah, it should be possible, but like not out of the box, I guess. Like you can write your custom code to like pull metrics from like Prometheus or somewhere, and then like or set up your own monitoring system, and then like evaluate and run. Yeah, limit as you mentioned. Yeah. Oh. Okay. So so if you need to, so the question was how you can upgrade the API gateway. Yeah, so yeah, like I guess it is similar to how you update all the other software, because uh, you can do something like a canary release as well, because if you have multiple instances of API 6 deployed, or like if you're talking at that scale, you need to have some sort of load balancer in front of that, and then probably do a canary release or something similar, so that like the traffic is not dropped in between. But the process is quite seamless. Like we do have a LTS version, and we also have edge releases. So most people like they stick to one particular version, and they take time to like update to a new version of API 6. But yeah, that's how we do it. Oh, yeah. Yeah, so one question was what kind of communication protocols we support. Uh, so all the different types of APIs, so like REST, gRPC, GraphQL, and like we also support multiple protocols. So we recently had a user who have been using API 6 for IoT applications. So that uses MQTT protocol. So it is pretty vast. And like another use case of an API gateway is like to convert between multiple protocols. So you might have a gRPC application, or you might have a GraphQL application, but your APIs or your client is in a REST model. So you would want to translate between those different kinds of API types, right? So an API gateway can be a facilitator for that. And the other question was about service discovery. So API 6 integrates with service discovery platforms as well. So like let's see, like So AP6 integrates with all of these platforms. So if you talk about Kubernetes, like AP6 integrates with Kubernetes default service discovery system. Let's see, like there should be some documentation somewhere here. Oh yeah. So you can see all these all these registries, all these different things that API6 supports. So yeah, you can definitely integrate with that, and like it will do service discovery. Yeah. You can also do it manually as well. Like so, if you have a YAML file where you are automatically populating your services or like your backend services, API6 can watch that and like do automatic service discovery. Yeah. Thank you. Thank you.
So thank you, Navendu, for this wonderful talk. So we are going out for a break, and Implement open source program to supply the cloud infrastructure. He's going to talk about Kubernetes cluster and other APIs related stuff. So yeah, here you go.
Thank you. Oh, hello everyone. Welcome to our presentation, and I'm Nguyễn Tấn Huy. I come from the Viettel Group, and I'm a cloud solution engineer at Viettel Group. My colleague is Nguyễn Duy Hiếu, but for some unexplained reason, he couldn't be here. And now today I will talk about the topic implement open source program to support the cloud infrastructure needed by a cloud provider Kubernetes cluster. And my presentation has the first one is overview, second one is problem, the next is solution for implementation, and the last one is value. Let's start. As you know, Kubernetes is a complex piece of software. Provisioning and managing Kubernetes cluster is a challenging job. To installing, configuring all the components of a Kubernetes cluster, such as Kubernetes, scheduler is so consuming time when you do manually. It means a situation when you have to manage hundreds of Kubernetes cluster. You provisioning in production environment and day-to-day to operate a cluster can be so tedious. Although there are some tools such as QADM, but it can manage full life cycle of the cluster. And here is cluster API is a Kubernetes sub-project and started by cluster life cycle 6. It's introduced declarative APIs that can be used to manage the life cycle of one or more Kubernetes cluster. So next, let me see a diagram of the component of cluster API. The way cluster API works is separated into provider, and what the provider do is that it have to make very modular. So that means you can plug in different infrastructure and different bootstrap machine. So we have the core cluster API controller is a core cluster API. It's managed. It includes API lifecycle logic. So all the lifecycle management is upgrading, rolling, update a machine, all that. Then we have the bootstrap, which is how to join a node in the Kubernetes cluster. Cluster API comes with a built-in bootstrap provider. So bootstrap provider based on the QADM project. When we have then we have the infrastructure provider, where you have your different infrastructure like environment, cloud, anything. For example, cloud, you have Azure provider and AWS provider, bare metal provider, etc. As last, we have controller provider, which are responsible for managing control plane machine. Managing can means operating control plane machine, make sure the Kubernetes components as scheduler are ready. As a core API includes the custom resource definition. The custom resource definition is a built-in resource that lets you can extend the Kubernetes API. So cluster API provider can provide and rely on some custom resource definition such as machine sets, machine deployment. So I want to describe the overall architecture of the various virtual cloud system before get into the meat of the matter. So architect consists of 3 main modules. Cluster management platform called CMP, the Kubernetes provider and OpenStack. CMP as a management module, communicating directly with the user through UI and receives the request and sends this request to Kubernetes provider. And the next, Kubernetes provider is a centralized management module that impacts the Kubernetes cluster. When receiving a request from the CMP, Kubernetes provider will send it down to the OpenStack to create Kubernetes cluster. Yeah. And based on the cluster API provider OpenStack solution, to create a Kubernetes cluster, you need to create numerous other resources such as load balancer, server, but the information of the component is stored in the OpenStack. And OpenStack is a private cloud. So the CMP can get the information about the resource created below the OpenStack. So when users send a request to create a Kubernetes cluster, the request will be sent to Kubernetes provider and it is to send to the OpenStack. And here is the network model of our architect. HVM of user cluster will be plugged into two VPC. One VPC is a user VPC, and the second is provider VPC. For the request that require go out to the internet, they will go through a router and go out the internet. And for the requests that require administrative and interaction with the OpenStack, it will go through the provider VPC. And to load balancer the API server of masternode, we use a load balancer attached to a VPC and expose it to the internet through a flapping IP. So our architecture is resolved in some problem later. The first, there were a lack of transparency of our system. When customer has a destructive behavior, is harmful to the system, such as they delete a resource, apply a file YAML, we can know, and customer can completely blame the supplier. Additional is it will take a long time to determine which resource is having a problem. When they an issue with the client infrastructure, which impact the customer experience, and the customer will not be satisfied. Another considered issue is lack of information. When a client sends a request to create a Kubernetes cluster, and the system dies successfully, all they receive is a notification that the cluster has been created successfully. The system can tell which resources are being created accordingly. And the customer will be able to update, revise, estimate, develop in a timely manner, since they don't have the information about them. And from that, the third problem is the calculation of the cost of using customer. User cannot know what they have paid for. And another issue is a complex network model. The issue affects both customer as well as service provider. And now and I will talk about our solution. And instead of using cluster API provider OpenStack, we custom and design a plugin named Cluster API Provider Vitel. The plugin can code to the CMP to create a Kubernetes cluster. Our CMP can create resource similar to OpenStack. As is our new architect. User send a request to create a Kubernetes cluster to UI. The CMP receives the request and send it down to Kubernetes provider, and then it will go back to CMP to create a related resource to the cluster API provider Vitel. And the the information of the resource used to create a cluster, such as load balancer, server, volume will be stored in the database of CMP, and it can push to the user through UI. With that, it's possible to show the customer the information of the resource created. And it's, now it's here the new architect model network. HVM of the user cluster are plugged in user VPC, and for other request to export to in the internet or connect to CMP API, it through a router, and we still use a load balancer to load balancer the API server of masternode. And to custom cluster API provider Vitel, we follow the cluster infrastructure provider contract of the cluster API and the machine infrastructure provider contract of the cluster API. We have defined the Vitel cluster template, Vitel machine, and Vitel machine template. In the API type, we add the field spec and status. Spec field is define the desert status, and the status field we define the offshore status. In the API Vitel cluster type, we have spec field, control plane endpoint. It's the endpoint for the cluster control plane and other object. And at the status field, we have a required field ready. It's used to indicate the provider specific infrastructure has been provided. And in the Vitel machine type, we have spec field provider ID. It identifies the UID of the provider machine instance. And as the status field, we have required field ready and other optional field such as file reason, file message. And we have defined a process here called reconciliation. The provider must watch for new update and delete result and respond accordingly. And so we have a role-based asset control. It's okay. And now in more detail, we define four main custom resource definition. Is Vitel cluster, Vitel machine, Vitel cluster template, and Vitel machine templates. At the Vitel cluster, we have defined the component of Vitel cluster, such as the VPC, subnet, region, load balancer, security group, listener, API server port, control plane endpoint, and in the Vitel cluster, we have defined the Vitel cluster spec and Vitel cluster status. And at the Vitel machine, we have defined the component of a Vitel machine, such as server, region, image, volume size. And the Vitel machine templates, it have the cluster API provider Vitel can integrate with other cloud provider. So it's the state transition when you create a machine. When machine creates a bootstrap provider was a machine in pending status, and machine controller set the data script name from bootstrap config. As the next status is provisioning. The infrastructure provider start or create infrastructure for machine, and when infra is ready, is set the status is ready. It's like status is provisioned. And when the status of machine infrastructure ready and the machine controller will set the machine status phase provisioned. And now when is the controller of our cluster API provider Vitel, when cluster API provider Vitel run, it will run two concurrent reconcile stream. It's a cluster and machine. The cluster reconcile stream will create and assure the cluster infrastructure is ready, and the stream of reconcile machine will wait for the cluster infrastructure is ready. At the reconcile of cluster, we will create a VPC, create subnet, create a robuster and another other object. It will assure the cluster infrastructure is ready. It will set infra cluster status equal to and cluster status equal to. Then the reconcile machine will start create the object. It creates volume, creates server, and load balancer member, and another object. When the other object is created, it will set the machine status infrastructure equal to, and the status and state is provisioned. Yeah. The use of the new solution has been brought many benefits to our cloud platform. It can provide sufficient information to user when user send a request to create a Kubernetes cluster, and all the information of the relative result is can push to the UI, so the customer can see all the information. The second is it will solve the pet problem, and customer will know what the next the new solution will assure transparency for customer and system. And the last, it will increase user experience when they use our cloud. Yes, thanks for your attention. Anyone has a question? Thank you.
Thank you, Hep, for this wonderful talk about Kubernetes. Hello. Yeah, welcome back. So now in the next session, that is going to be led by Ankit. He's going to talk about DevOps is dead. Yeah, that's what. So over to you, Ankit.
Thank you, Preet. You'll have to excuse my voice today. My throat decided the worst time to not work. But I'm Ankit. I'm a lead platform engineer and consultant for ThoughtWorks. I've been in the DevOps space for most of my career. And most recently, I've been leading teams to build self-service cloud infrastructure platforms for our clients here, mostly in Singapore. So today's talk is about, well, the state of DevOps and where we are, what's next, and how did we get here. So it's this title is a bit clickbaity and slightly controversial intentionally, but it's also extremely popular title that a lot of people are throwing around these days. Have you heard of Is DevOps Dead? Have you seen any of these conversations before? So, okay, so nobody's heard of somebody proclaiming that DevOps is dead. All right, okay. So let me introduce you to this new debate happening in the platform engineering side of things. So what's happening is probably a marketing department gone crazy. What the actual question is not is DevOps dead, but is DevOps no longer relevant, and is platform engineering a replacement for DevOps? that's what people are actually positioning. So you'll see a lot of content that's titled DevOps is dead, long live platform engineering, etc., etc. Some people are doing it to evangelize platform engineering, which is good. Some people are doing it. Some people are explicitly refuting it, which is also probably good. So have you heard of platform engineering? Okay, so 1, 2 people. Okay, so I'll just poll the 2 people. Do you guys believe DevOps is dead? So there's a no from over there, Anna. Right, and a non-committal response from here. So, okay. So let me start off with answering the question before I get into the details. Yes, DevOps is dead, but probably just as a job description in a team name. And I say this as an ex-DevOps guy. Do you guys have DevOps in your job titles, or you have colleagues who have DevOps in their job titles? Right, okay. And have you experienced organizations where they have large, long-lived DevOps teams? Have you interacted with a DevOps team before? The name of the team is a DevOps team. Yeah, I see a few nods, so I'll take that as a yes. So most probably and most hopefully, these teams will no longer be called DevOps team, and everybody will change their job description from DevOps engineer to platform engineer. And that's probably a good thing, because if you're in my camp of what is DevOps, and it was never intended to be a team or a job title anyway. So also DevOps is not dead. DevOps remains the North Star culture of enabling teams to own features end-to-end in their entirety of their design, code, test, build, deploy life cycle. And platform engineering builds upon DevOps and enables DevOps. So like a good politician, I've given you both the answers. A good consultant, so since that's my job. Before we get into what's platform engineering, I'd like to show you a visualization of data I pulled from LinkedIn about the transition of people from the DevOps job title to platform engineer. So this is some data. As you can see, the evidence is quite compelling of the number of DevOps engineers who are transitioning to platform engineers. So it is happening. But what is platform engineering? And why do we need it? So let's look at it backwards. Like, what are the current dysfunctions or pain points in the engineering process that we are trying to solve with this relatively new thing, which is platform engineering, and why are people claiming that it's a replacement for DevOps? So if we look at some of the common pain points that people are trying to address, rightfully so, and you may or may not relate to some of them, but I relate to all of them, is on a day-to-day, as a software engineer trying to deliver software features, one of the biggest dysfunction and pain point and wastage is just waiting. You've probably all had an experience of having to write up a Jira ticket, send off an email, DM a friend in another team, because you need some dependency service by some other teams to be able to do your job. So you're sat there just waiting for somebody else to do their job, because you're coupled with them and dependent on them, so you can do your job. And this means you may have to sort of context switch a lot, bring in some other work, jump between tasks while you wait for your dependencies to be fulfilled. The other thing is cognitive load. I learned this term from the book Team Topologies. It's a really good way of describing load. It's not about the volume of work, it's about the human brain's capacity to be able to simultaneously in parallel hold only X amount of context and be able to do only X amount of work. So cognitive load happens when, for example, say you need some configuration change in the service mesh layer. You're a product engineer, you're an app developer, and the service mesh team says, hey buddy, we are too busy servicing some other requests at a higher priority. Why don't you just make a PR to our repo? And so to make a 3 lines of config change, you begin a 3-week journey learning everything from clusters to orchestration to networking to service mesh to be able to make that change. That's completely extraneous to your actual day job, and that adds to your cognitive load and you're spending time away from what you should actually be doing, which is writing features. The very interesting one is also some heroic unicorn figures in teams. We often have teammates who have like really high potential, really talented, who have somehow figured out everything related to the app we are building and also all the surrounding infrastructure layers and our dependency and how CI and CD works and all the tools we depend on that nobody really knows. So if anybody's stuck on anything, you always end up going to these really talented few. This also is a way where cognitive loss is masked and burdened on a select few people. This is also a massive waste, even though it can look good, is because these are probably your most talented folks in the team. You probably want most of the energies directed at value-add work. And the other is, of course, everybody's favorite, a whole bunch of meetings. Meetings are symptoms of team interactions not set up correctly. If you're having to go into a meeting to explain to other people what you need and there's a whole bunch of back and forth, it simply means the interface between two teams, there's something wrong there. So you can end up feeling like, okay, I was hired to be a feature development on an app, on a product. I'm really excited. I want to learn, master my craft, but all I've done for the last 3 months is learn about all the peripheral layers and the organizational structures and everything else other than actually mastering my craft, building my career, and driving business value. So you're left feeling like, and I just want to do my job. If you feel like that, it's not uncommon. This is a fairly old but still relevant survey. The Stripes developer coefficient from last year is also quite relevant, or 21, I forget. But essentially it says that waiting, struggling with bad tools, which is cognitive load, waiting on requests, etc., are the highest reported area of waste and pain or dysfunction in the software engineering process. Okay, so how did we get here? I'll try to speed along because I don't know if I'll be able to squeeze everything in the 15 minutes that remain. So, okay, how did we get here? Well, in the beginning, there was the Big Bang, and then nothing interesting happened for a long time, except around the mid to late 2006, two really interesting things happened in our industry. The first was, okay, Dev and Ops were doing their thing. They were separate siloed units, and Dev would build or at least code and hand things over to Ops. This is a story all of you are quite familiar with, so I won't harp on about it. But then what happened in this 2005-2006 timeline is also microservices. What started happening, and what that meant was that now the ops team who had that one bash script or systemd unit file to manage one monolithic application across one server or just rinse and repeat that across multiple servers, had to deal with a massive distributed 1,000 application things running on complex clusters, needing orchestration, etc. So the ops team had to scale up to respond to this extra operational overhead of managing the same systems. And they had to build out sophisticated operational tooling. And just to give you how massive this landscape of operational tooling is, this is probably 30% of a screenshot from the CNCF landscape page. All of these tools are what classically belong outside of a product engineering team, right? So who owns these tools? More often than not, it's assumed that all of these things are bucketed in that infra ops platform kind of team layer. So there's increased overhead and also increased sophistication or complexity in operational concerns. What that means, so that's one. The other thing that happened was also somewhere around the same timeline, people realized that for quality and speed, we need dev and ops to work together. Specifically, we need developers to own a little bit more of operational concerns. How do we do it? Nobody knows. And nobody, like a few people did it right, but quite a few people did it in very interesting anti-patterns. These are two of my favorites, and these are ones that I have encountered most. The guys who wrote the book Team Topologies actually document these things in 2013 at that link over there. So the first one is dev doesn't need ops. So you say, okay, you build it, you run it, but run what? Like run everything down to the hardware layer? That's almost impossible because of the sheer amount of complexity you end up owning. So over here we have ops that are embedded in the team or part of the team, and there's no real ops support. And the other even more popular one is over here where, okay, let's just call the ops team a DevOps team and be done with it. Now we're DevOps. This is the one I've seen more often, and this is why I feel DevOps teams exist, and hopefully DevOps teams will die soon. Not to say that we won't make the same mistake with platform engineering. So what happens in both these kind of anti-patterns is on the left, you get extremely high cognitive load, and you need those highly talented and unicorn engineers to be able to deal with anything, because you just have so much complexity you own. You need to understand all the layers beneath your application to be able to you build it, you run it. And what happens over there is you're just stuck waiting and dependent on these massive ops or DevOps teams that are servicing the entire organization. And almost always a DevOps team will be a bottleneck to an organization. It's a given. Like at a scale, if you have one team doing ticket-based work raised by others, it's going to be a bottleneck for your organization. I don't know how many of you have struggled to get your work prioritized for an ops or infra team over other teams. Or, hey, I need this database. Can you, I'll take you out for a beer. Can you get my work done first? Okay, so what is platform engineering and how does it help? So this is Evan Bocher's definition of what is platforms. He wrote this back in 2017. There's an article on martinfowler.com. You can check it out. We don't need to read it. We need to just look at 2 words for the purpose of today. This is all interactions are self-service, and it's a compelling internal product. So self-service and product, as long as we keep those things in mind, we can solve for the previous anti-patterns and actually try to make DevOps work. So instead of something like this, if we could have a team that sort of exposes all of these operational concerns for product teams, hey, I need a service mesh configuration, I need a cache, I need a database, in a way that these product teams can self-service it, while also at the right level of abstraction, they're not trying to figure out how caches and RDSs work and what subnet it should be, what security group, blah, 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 that product teams don't need to worry about, and expose it as a self-service API. If we can move to this kind of team topology, it would hopefully help both these types of squads be DevOps. What this means is I'm now enabled to own my feature end-to-end because all the layers underneath that I need to manage are exposed to me at the right level of abstraction. I don't need to worry about all the details and all that. And the below team is the DevOps team, because just like any other software engineering team, this team also owns their APIs that they offer to other internal customers end-to-end. So I think we need an example to sort of really understand what's going on. So a very common developer journey is, hey, I need data persistence, so I need a database for my application. At this point, what happens? Usually what happens is we reach out to another team, raise a ticket or phone a friend or whatever, and say, hey, can you please give me a database? And they say, hey, I'm inundated by 3 other teams that need XYZ, and also VAPT is happening and audit is going on, blah, blah, blah. You got to wait a week or 2 before I can provision that database for you. So you end up waiting a while until the database is provisioned. It really depends on when that team gets your job done. The alternative is dev doesn't need ops, the other anti-pattern, where you try to, the team says, okay, I can't unblock you now. If you really need it, just do it yourself. Go to AWS console and click ops your way to a database. So you do that, except 3 days later, security comes knocking and say, hey, buddy, where's the encryption configuration on this database? And you say, I don't know how that works, man. Can you help me out? And then you're back to square one. So the alternative is a model like this, where a platform team is internally exposing a database as a self-serviceable infrastructure, and the product team is consuming it. The platform team takes ownership of all the layers that make it self-service. So it's productizing this self-service API. It's saying, okay, you don't need to worry about the encryption configuration. You don't need to worry about the backup configuration. You don't need to worry about security and compliance. All of that is baked in. Just read these documents and consume this thing. And the product team says, okay, as a product team, I'll probably just need to figure out what version of the database I want and how big do I want it. That depends on my user traffic. So that's the only configuration I will own. Now this team can end-to-end own this configuration, because say they need to upsize their database, they can self-service that themselves. And say if there's any change in any other layer, you could have many ways of product teams consuming updates pushed by providing teams a platform team. Semantic versioning could be one of them. So you end up with this model where you have DevOps teams exposing self-service APIs to other DevOps teams. And I don't mean teams that are called DevOps. I mean teams that practice DevOps, because they can own their stuff end to end now, because this doesn't cost the 50 years of learning to be able to own it. Okay, and that's about it. Uh, so in conclusion, DevOps is not dead. Platform engineering should enable, is based on DevOps and enables DevOps. That's my LinkedIn if you guys would like to connect. I think we have maybe a minute for questions or something like that. But thanks, that's all from me. Okay.
So basically you say the platform team should have all the resources, so the documentation and even AI that's on top of, say, the AWS.
Yeah.
On top of AWS.
Yeah, yes, but it doesn't have to be a REST API. It can be, here's a README, here's some config you can push to your GitHub Actions workflow, and this workflow will provision a templated, every security compliance practice baked in database. So it doesn't have to be like a HTTP API or something unnecessarily complex. The most prominent way I've seen folks do it, which also feels like will probably win out, is defining operator-based models and defining things as Kubernetes CRDs, because then that lets you sort of offer APIs really, really cheaply. So, okay, define a database type in your cluster, and then the cluster makes that database real in AWS land. So you can say kubectl get cluster, kubectl get database, kubectl delete database, etc., because it's a custom resource then. Sorry, does that answer your question?
It does, yeah. But then it's more on each document.
Actually, yeah, that's a good question. I think it could be either. So this is a really compressed and simplified version of all of this stuff. What you probably want to do is talk to who your customers are and see where they want to interface with you. Do they want to interface with you at a human API level where you copy paste some config into an action? Do they want a CLI tool like a Heroku kind of thing to provision your platform infrastructure or something like that? So part of running a platform team or platform teams is also having a product mindset and then doing that research, okay, what will work for my organization?
So if you want to start a platform engineering team,
you need to find a product owner, then you need to talk to your users, then you need to prioritize the most common pain points, and then you need to create a minimum viable, super lean platform and test it out in the real world with your real users. And you need to find one team that will evangelize your platform for you. So it's quite similar to product engineering in that way. Anything else, folks? Yes? Well, we do it for some of our clients, which I can't probably mention. And I think a really good one for you not to talk about my company, though you can find some resources on ThoughtWorks that are quite good, is a lot of stuff that comes out of Spotify. They have been on their platform engineering journey, and they have sort of a framework for building internal developer portals out there as well, or tool at least. So you can check out things they publish as well. I think any organization that's like more than 300, 500 engineers will have some platform engineering effort going on, or should. Sure. Do we have time? Sorry, do we have time? Okay. Yeah, sorry, go ahead.
frameworks out there to start with,
So it really depends, because with the platform, if you could be solving a lot of customer needs, customer being the internal product team. So which need you're trying to solve will mean there is probably a tool that exists to solve that need. So specifically, because this is an infra provisioning self-service example, you could check out Crossplane, and you could check out Open Application Model, which is something coming out of Alibaba and Microsoft. So they have Crossplane is specifically designed for its infrastructure as code, but it makes exposing an API to your consumers first class citizen of the tool. For example, I would argue Terraform does not do that yet. And then Open Application Model is a very holistic but very opinionated model for how product teams or developers should interact with the platform. What are the components of the platform and how it should sort of work. Yeah. I think we are out of time. We can talk later, or you can just connect with me on LinkedIn or something. Yeah. Thank you.
Thank you, Ankit, for this insight. I'm pretty sure still people are having in the dilemma that DevOps is dead or not yet. So maybe they can get in touch with you offline.
Thanks, Paul. I'll leave it here.
Okay, welcome back. So we have Paul as our next speaker. Paul is having vast experience in research and development and big data as well. So today he is going to talk about K-Raft, the new thing for Apache Kafka. So over to you, Paul.
Marvelous. Thank you very much. Thanks for coming along, everybody. This was a talk that I volunteered at the last minute because we had a spare slot. It was based on a 40-minute talk I gave at Apache at Apache Con last year in the US, so I hope it fits in the available time that we've got. I'm the open source technology evangelist at Instacluster, so I talk about quite a lot of open source technologies, but Kafka is certainly my favorite, and it's the first one I actually learned from scratch when I started my job at Instacluster about 6 years ago. So it's the one that I've built up a lot of experience of over the years, and the change from using Zookeeper to the new K-Raft protocol is perhaps one of the more significant changes under the bonnet for Kafka in my experience. And I think it probably fits in quite well with the previous talk as well, talking about platform engineering Kafka is certainly one of the more pervasive pub/sub middleware technologies, and the best known open source one that's been used by just about everybody now around the world. So Kafka abandons the zookeeper on a K-raft. That's more or less the story. So Apache Zookeeper was quite a well-known Apache open source project for distributed systems coordination, and it's used by a lot of Apache projects, including Kafka, and it's actually really good. At ApacheCon last year, I actually gave a talk about why Apache Zookeeper is so good still, and then the next talk I gave was about, well, actually you don't need it for Kafka anymore, so it was a bit confusing, potentially. So this story is going to be assisted by a few train pictures, and this is one I took in New Orleans last year at ApacheCon. So InstaCluster provides a managed platform for big data, open source technologies. We've got technologies for storage, streaming, analysis, search, and orchestration. Yesterday I talked about Cadence. Today I'm talking about Kafka. So that's our main streaming technology. And up until now it was three components: Kafka itself, Kafka Connect, and Zookeeper, which we all ran as managed services. So Kafka, just briefly, is a distributed streams processing system. It allows distributed producers to send messages to distributed consumers via Kafka, which is a distributed cluster with multiple nodes and multiple things going on in the nodes, primarily topics and petitions. Kafka topic petitions enable massive consumer concurrency. Essentially, you've got producers sending messages to one or more topics. You've got consumers consuming from one or more topics. And the way that the workload is balanced over consumers is you can have more than one consumer in a consumer group, and each consumer can consume from one or more petitions. So that enables high consumer concurrency. This graph shows throughput on the x-axis versus petitions on the y-axis, which is in millions. So the catch with Kafka consumers is they're single-threaded, well, at least the default Kafka consumer is single-threaded, which means you need to increase the number of consumers as the consumer response time or latency increases. So, for example, if you want to achieve a throughput of 10 million messages a second and your consumer has a latency of 100 milliseconds, you're going to need 1 million petitions in that topic, which is a lot of petitions. Petitions are expensive. They have replication and meta management or metadata management overheads associated with them. Without going too much into the detail, the real problem is that the Kafka cluster itself has to manage the topic partition metadata, and it also has to cope with the replication, and a replication factor of 3 is quite common in production Kafka systems, so that means each message you send to a topic has to be replicated on 3 other brokers as well, which introduces quite a significant overhead to the whole system. So how does Kafka work? Basically, it has a controller. The Kafka controller does all the control plane stuff, all the metadata management. There's only one active controller at a time. Each broker can potentially have one controller, but there's only one active over the whole cluster at a particular point in time. The Kafka controller manages the broker topic and petition metadata. It's basically the brain of Kafka. Most people don't even know it's there. If you're using Kafka as a managed service, you don't even need to think about the controller side. That's all handled by Kafka for you and the managed service provider normally. But that's actually how it works. Which controller is active and where is the metadata stored? Well, essentially the answer to that up to a few years ago was in Apache Zookeeper. Zookeeper is used for the controller election and storing the metadata. Zookeeper has the concept of an ensemble, which is just really a cluster of zookeepers. So you have typically 3, you can have more, but probably not more than 7. Again, there's only one of those which is active at a time, the leader, zookeeper. The active controller from the Kafka cluster communicates with the zookeeper leader and keeps track of the election data and the metadata as well. So that's pretty slow. That's quite a big bottleneck. Zookeeper isn't great in terms of write scalability. Metadata changes and recovery from the failover are quite slow. Reads are pretty fast due to caching in the Kafka cluster itself, though. So it worked okay. I mean, you could get some pretty big clusters up and running and with reasonable numbers of petitions. So the new KRaft mode is something that's just come along in the last couple of years. KRaft is Kafka plus the Raft consensus algorithm, abbreviated to KRaft. So the Kafka cluster metadata is now only stored in Kafka, so it's fast and scalable because Kafka is fast and scalable. The Kafka cluster metadata is replicated to all the brokers, so failover is a lot faster as well. The active controller is just the quorum leader, and it's using the Raft protocol to elect the leader internally as well. So there's no dependency anymore on the external zookeeper. So we had a couple of hypotheses that we wanted to test when we started out looking at the new KRaft mode in Kafka last year. We were interested in whether there'd be any impact on the actual data workload performance, and we assumed that there probably wouldn't be. We guessed that we'd probably see similar results between Zookeeper and KRaft just for the actual data workload. But for the metadata changes and recovery from failover, so metadata performance, we knew that Zookeeper was pretty slow for some of these operations, and we assumed that KRaft would be faster. That was the promise, anyway. We knew that using Zookeeper, there were quite a lot of limits on how many petitions per cluster you could get out of Kafka, and we assumed that using KRaft there'd be a lot more, hopefully. And with the robustness aspect, we knew Zookeeper was pretty robust. There weren't many situations where Zookeeper caused any problems, and Kafka itself was pretty reliable using it. But this is an unknown feature of KRaft because it's a new feature. It's only just recently become production ready. In fact, it's been available for a while now, sort of as a proof of concept. People can try it out in a developer context and test it out. But we weren't sure whether it was going to work particularly well in a production environment or not. So basically, I did a couple of experiments using a fairly early version that we had available in our managed service. The first experiment was whether the data workload performance would be different or not. So we assumed that there'd only be minimal or no difference between Zookeeper and KRaft message throughput. And this is purely looking at the producer workload at this point, actually, as well. Why? Well, we know that Zookeeper and KRaft are only concerned with metadata management, not the actual data workloads. Kafka producers only need read-only access to petition metadata, so they should just be as fast, basically. So how did we do it? We set up Kafka 3.1.1 on some identical AWS nodes with an RF factor of 3. And what did we find out? Well, okay, it confirmed our suspicions that there was actually no difference in throughput whatsoever, which you can see there because you can't actually see the blue line. It's hidden behind the orange line. So, so the bottom axis here is the number of petitions. So we managed to get up to about 10,000 petitions in the cluster. The throughput is the y-axis. Yes, sorry, no, petitions is on the x-axis. Yeah, throughput on the y-axis. And yeah, there's an identical throughput, basically. There is a cliff. This is something we've seen before with Kafka. When you hit a certain number of partitions, you actually get a reduction in throughput. And this isn't too bad compared to some tests we ran about 2 years ago where the throughput started dropping off at about 100 petitions. You only start seeing this drop off in throughput now around about 1,000 petitions. So that is still something to watch out for, though. Again, petitions versus latency in milliseconds. Not surprisingly, as the throughput drops, the latency also starts skyrocketing to the point where it would become unusable, which for a low latency system like Kafka is a real issue. So you want to avoid that if you can. For the second experiment, we had a look at petition creation performance. How long does it actually take to create a larger number of petitions? So how many petitions can we create? Can we actually create more on a KRaft cluster compared to the older Zookeeper cluster or not? How long does it take to do this? So a few simplifications for this experiment. We used an RF of 1. Otherwise, because of the replication that goes on with topics and petitions, the background CPU can be quite high when you have a high number of petitions and a high replication factor. With an RF of 1, though, there's actually no replication and there's very little background CPU going on. We could have used a bigger cluster, but for the sake of the time and experiment, we just set the RF to 1 for this one. And then there was still about 50% background CPU load on the clusters with 100 partitions and no workload going on as well. We tried a few different things to create a large number of partitions. The first approach was just using some of the Kafka tools to create a topic with lots of partitions straight off. Then we tried using the alter command to actually just increase the number of partitions on an existing topic incrementally. We tried curl with our inbuilt provisioning API because we were having problems with timeouts with the first two options. And finally, we tried a fourth approach, which was just a simple script to create multiple topics with fixed number of partitions each. However, there was a problem with all of these. All of them actually failed eventually, and the only difference is really how soon the failure occurred. And after some of the failures, disturbingly, the Kafka cluster was basically unusable even after restarting the Kafka process on each node. So something was a bit strange. This graph shows the number of partitions on the x-axis versus the creation time in seconds on the y-axis. Zookeeper basically has a linear time for creating partitions, so the more partitions you want to create, the longer it's going to take, up to a point where there's an eventual timeout which stops you creating anymore. With using Kraft, it's constant time, so it's a lot faster, which is the orange line on the bottom there. So it's actually very easy using Kraft to create lots of partitions, but still with the eventual failure occurring, mostly due to timeouts as well, which was interesting. So the other approach we tried was the incremental approach. So this is the time per 1,000 partition increments, which does increase with the total number of partitions in the topic. Zookeeper is the blue line, so it is a lot slower than Kraft. Kraft is actually taking some time, though. So it's basically a slow process still to create a large number of partitions, and still we were getting eventual failure. So the initial conclusions were it's certainly faster to create more partitions on Kraft compared to Zookeeper. We were hitting a limit of around 80,000 partitions on both Zookeeper and Kraft clusters, and Kafka ended up failing. So it's actually very easy and quick to kill Kafka on Kraft. Just try and create a 100,000 K partition or more topic, and something inevitably goes wrong. So another experiment we did was the performance of the metadata workload. For example, reassigning partitions. So a common Kafka operation, for example, if a server fails, you can move all of the leader partitions on it to other brokers, and there's a simple command to do that. And our tech ops people are doing this all the time for customers. You run it once to get a plan, and then again to actually move the partitions. So moving partitions from one broker to another 2 brokers was the experiment we performed, with 10,000 partitions and a replication factor of 2 this time. And we got the answer to life, the universe, and everything, which, yeah, is 42. But what's the question? Well, okay, so the question is how many seconds does it take to reassign 10,000 partitions using Kraft? 42 is the answer. So it does take quite a significant amount of time using Zookeeper to do the same operation at 600 seconds. That's quite a significant overhead at that point, not having one of your nodes available on a cluster. 42 seconds is certainly a lot better. Although just noting that there was actually no partition data for this experiment. So in real life, it's quite likely that the time to move the data is going to be dominant as well. Experiment 4, this is the one that I was really excited about. Everyone had been saying, I can get millions of partitions with Kraft. I mean, millions of partitions is probably a silly thing to be trying to achieve, but for the point of view of science and doing an experiment, we still had that goal in mind that, yeah, if we can hit 1 million partitions, we will have proved that Kraft was actually doing what it was advertised to do. So this is my final attempt to reach 1 million or more partitions on a cluster, again with RF equals 1. I didn't want to have an enormous cluster to do this at the time. To achieve it, we had to sort of cheat a bit. We used a manual installation of Kafka 3.2.1 on a large EC2 instance, so it's not actually a cluster at this point either. And we were still hitting the limits at around 30,000 partitions, so this is the sort of error that we were getting. It was a bit of an odd one. It's not one I'd seen before. It was a map failed error, something to do with the Java runtime and the available memory. A slightly odd error because we knew we had lots of spare RAM. We hadn't encountered this sort of error before on very large clusters either. So we tried increasing the amount of RAM. We tried things like increasing the number of file descriptors, which we knew was actually quite important. And again, because I was just doing this myself as an experiment, we weren't relying on our managed service version of Kafka, which has all these configurations sort of carefully configured for customers. I had to sort of recreate some of our settings. So yeah, typically we do have lots of file descriptors. 65K is the default on Linux, and for Kafka you need a lot more than that, basically. But it still didn't work. So yeah, we had plenty of spare RAM, but we were getting this out of memory error. Googling this type of error actually did discover what the problem was. On Linux, there's a thing which determines the maximum number of memory maps that a JVM can, or a process can have. And again, the default was only 65,000. And because Kafka every petition uses two map areas, that actually limits you to about 32,000 petitions, which was actually roughly the number we were hitting the limit at. So we set this to a very large number and tried again. Did we reach 1 million? Well, sort of. Yeah. So we managed to hit around 600,000 petitions just on the one Kafka broker that we were experimenting with, and by inference, for a 3-node broker, we would be hitting over the 1 million petition mark, about 1.9 million petitions we estimate. We have actually redone this experiment since. This is a bit out of date with our new managed service with KRaft. In fact, that's exactly the sort of number that you can get with the KRaft mode. So that's a lot of petitions on Kafka. Typically our production customers only have hundreds of petitions on a Kafka cluster. Millions is sort of interesting theoretically, but I don't think there's much practical application at this point in time. Okay, what about the batch error? It's still actually painfully slow to create this many petitions due to the batch error when you're trying to create too many petitions at once. This actually turned out to be a real bug. The quorum controller has a limit to how many things it can handle, basically, with the maximum batch size. And the promise is that it will be fixed in 3.3.3, but we haven't tested that yet. So, just some takeaways about KRaft. It's fast for data workloads. There's no difference, in fact, to the Zookeeper mode. It's certainly faster for some metadata operations that we've tried. You can have clusters of more petitions, potentially more than 1 million. You still have to watch out for some of the operating system JVM configurations to support clusters with more petitions. And yep, trust your managed service provider, because they've probably done the experiments, as we have, but we're constantly learning. So should you use Kafka KRaft mode yet? Well, yes, 3.3.1 is production ready. And by 4, which will be next year, there will actually probably be no Zookeeper mode anyway. So it's probably time to start exploring the Kafka KRaft mode. We provide Kafka 3.3.1 in public preview, I think, at the moment. And you can test out a free trial for a couple of weeks using some quite reasonable sized Kafka clusters on various cloud providers. We support AWS, Google, Azure, and a few other ones as well. So we're providing that as a public preview at the moment rather than sort of final general availability, because we are still learning how KRaft will be working mainly for our tech ops people. So it's giving them some experience, and it's also giving our customers experience in using Kafka just in a development context initially. And that's it. So that was a 40-minute talk, shrunk down to 15 minutes. So there's a lot there, but I mean, hopefully that gives you a bit of an overview of the new KRaft mode, and it will be the future of Kafka. I don't think there's much choice about that. So thank you very much. Oh, any questions, I guess? Well, there's lunch next, so ask me over lunch if there's anything you'd like to know about Kafka in general or KRaft in particular, or anything. Yep.
Okay, thank you for. So now I think we are taking break, and in the second session, half, we have few other important session lined up. So meet you again then. Bye.